And the next thing is a dependent samples t-test. Guys, just from the nature dependent, it says we don't have independence, so we're not running a two-sample t-test or an independent samples t-test, as I illustrated in one of the previous videos. We have a dependent samples t-test. Sometimes we call this a matched pairs t-test. Now let's see the difference. In an independent samples t-test, we have one population, we'll just call this population number 1, and a population number 2, and these two things are independent. In other words, the measurements that we get from population number 1 do not depend on the measurements that we get from population number 2. This thing has a mu1 and a mu2 and a sigma 1 and a sigma 2. And to take a look at that, we take a sample from both populations. And conduct either a pooled or unpooled two-sample t-test. Obviously, if we could prove, or at least know from theory, that the variances are equal, then we would run a pooled test. If we can't assume that, we would run an unpooled test. I think it's always safe to run an unpooled test. Now, what's the difference in an independent and a dependent? A dependent samples t-test, still you can think about this as being population number 1 and this being population number 2, but the measurement over here is in some way related to the measurement that we take over there. The classic situation that we run into with the dependent samples t-test is when we do a pre-test on a student and then a post-test on a student. So we bring student number 1 in, let's call him Jim, and he takes a test. We invoke some sort of treatment, an experiment, whatever it may be, bring Jim back in and take the test again, and we get a second measure on Jim. Guys, that's called a dependent samples t-test. We don't have independence for obvious reasons. We're measuring the same person. So where in the independent samples t-test we have two independent samples, or two independent populations, in this case the second population depends on the first population. The illustration that I want to use here is this. I typed it out, and actually I found this. Okay, so Power Score and Preparation, guys, I'm not making this up. Okay, sells its ACT improvement program for $350. Their program includes 12 hours of intense instruction, their words, not mine, and test preparation, and guarantees a 3-point improvement. Okay, so we'd like to test their program. So what we do is we have Dan, Frank, Alice, Joy, Bob, Phil, and Kate go take the ACT. Afterwards, we have them sign up for Power Score and Preparation Test, pay the $350, go through the intense 12 hours of instruction and test preparation, and hope their program works to get a higher ACT afterwards. Now, this works different in that, all right, let me, what we focus on is we focus on the difference. So let's get rid of this stuff right here. I don't want to do that. I just want to delete the... Well, that was just lovely. Alright, let's see if we can do this and act like I've got some sense. So I want to insert a row, not there. And then I will come in here with the difference. Alright, so the first difference, Dan improved his score by 2 points. Frank improved his score 0 points. Alice improved 4 points. Joy improved 2. Bob improved 2. Phil improved 5, good for Phil. And Kate improved 1. Guys, our test now has tunnel vision on this. So we're looking at the difference in the scores as the measurement and not the scores as we do in a 2-sample t-test. Alright gang, let's show you how we actually make this happen. First of all, I want to go back here. I was doing that for illustration, but I wish I hadn't. So I'm going to do a little trick here. You guys will be completely and totally amazed. Actually, you won't. Alright. Now I'll tell you what I'm going to do. I'm going to shut R down because I want to kind of start from scratch, and sometimes I like to call things the same. So let's bring R back up. Computer's running really slow, man. I don't know what's up with my computer. Okay, so I'm going to enter the data this way. I'm going to use the C function. So my pre-test scores I'm going to enter. So I'm going to enter 27, 18, 18, 23, 26, 17, and 19. And my post-test scores I'm going to 29, 18, 22, 25, 28, trying to help you guys out, so when you type, and 20. Okay? So hopefully we've got 7. Now I'm going to set up my difference to be my post minus my pre. So I type my difference. My focus, just as I had before, is on 2042251. Okay? Well guys, let's go back over to the blackboard and I'll show you how this happens. It's actually semi-cool. I've lost my connection. And those of you that are doing the straight A fund, I know you can relate to the nuances with doing these lectures, but you know, it's kind of cool that I'm sitting here in my gym shorts just teaching my little heart away. Alright gang, first thing we want to do as always is set up our null and alternative hypothesis. And unlike before where we test the mean difference in the populations, here we're going to test that the mean difference is equal to 0. The alternative hypothesis, I would test mean difference not equal to 0. And I would always conduct a two-tailed test. In fact, guys, I would always conduct a two-tailed test regardless what kind of test I'm conducting. So alpha equal 0.05, probability of a type 1. Next thing is the test statistic. Guys, we have a test statistic, degrees of freedom, n minus 1. And this is the sample mean of the differences divided by the standard deviation of the differences divided by the square root of n. So we have some information that we need to find. We need to find the mean for the differences. We need to find the standard deviation for the differences. And we need to, find our sample size, which I think we saw that was 7. So guys, let's go back over and use R to create this. So first thing we want the mean of the differences, which is 2.286. Next thing we want is the standard deviation of the differences, which is 1.704. And I know it's 7, but let's just do this just because we can. So the sample size is equal to 7. All right, gang, so the test statistic is going to be 2.286, 1.704 divided by the square root of 7. Now, just put that in your calculator. I'm just going to grab my calculator and do this. And I get 3.56. Okay? Now, the next thing I'm going to want to do is calculate my p-value. Well, I know that my test statistics follows the t-distribution. Degrees of freedom 6. I've got my sampling distribution, and what was it, 3.56? So I need to find the area in that tail, but since I'm conducting a two-tailed test, that's equivalent to finding the area in that tail and adding the 2. So I need to find one of the areas, multiply by 2, or find the areas together. Okay, guys, easy stuff. Let's go back to R, so we know we're going to use PT. And it's going to find the area below, so I'm just going to put in the minus 3.56 degrees of freedom 6, and then I'm going to multiply that by 2 to account for the other region. So my p-value turns out to be, I'm going to write this down so I don't forget it, 0.0119. Okay, so guys, that's clearly less than alpha, 0.05. So we reject the null. So to get real dramatic and all visual here, so what we're saying is there's much more support from our sample that the mean difference is not equal to 0 than there is that the difference is equal to 0. So it appears that the test preparation program is improving test scores. But they've made the claim that the program will improve by 3 points. So what we now need to do is we need to create a 95% confidence interval for the mean difference. And if 3 is contained in our confidence interval, then you know what? We got to pat them on the back and say, well, you know what? It appears your program's working. If 3 is not in there, well, it would depend, and I'll tell you the situation there, okay? So, as always, the confidence interval formula consists of 3 parts. This is our point estimate, this is our t-critical, and this is our standard error. So guys, we should know from this that our point estimate is going to be the sample mean for the difference plus or minus our t-critical, degrees of freedom 6, times the standard deviation for the differences over the square root of n. So gang, at the end of the day, we've got everything we need except for this right here. Alright, so let's go use R to find that value. So what I'm going to use is QT 0.025, comma 6 to find the left t-critical. So that's negative 2.447. So I'm going to write some stuff down so we've got it when we go back over. And of course the positive is going to be if we would put in QT 0.975, comma 6. So the middle 95% of our confidence, I'm sorry, of our sampling distribution defines our 95% confidence interval. So the mean difference was 2.286. The standard deviation was 1.704. And we have 7 measurements. So gang, let's go back over here and see what I've been writing. So we have this right here. So I'm going to put this in my calculator, and I encourage you to do the same. So 2.286 minus 2.447 times 1.704 divided by the square root of 7. And I need to do that again. So it's actually looking pretty good for the company. The 95% confidence interval I get is 0.71 to 3.86. So since their claim of 3 is contained in our interval, we do not have statistical evidence to contradict their claim or to challenge their claim. Now, I told you that there would be a situation where we could have statistical significance, yet their claim wouldn't be substantiated. For example, what if we come up with a confidence interval that was this? That certainly supports our decision to reject the null, but this entire confidence interval lies below the 3, meaning that statistically it seems like scores are being improved, but not at the level of 3. What if we came up with something like this? Well, in that case, they'd be shortchanging themselves. 3 is not contained in our interval, but this entire interval is above 3, indicating that not only do we have statistical significance, it appears that the scores are being raised somewhere between 4 and 4.12 and 6.82 points. So they would be kind of shortchanging themselves in that the program is actually working more effectively than they're giving themselves credit. Well, guys, these things are really, really super easy to do on R. What we do is we run a t-test, and I want to run the pre, post, and I want to run paired equal true. So guys, when you run this, you're going to see some things that come up that coincide with what we got. Now, one thing to notice is our p-values and stuff are the same, within rounding. But notice that our test statistic is negative instead of positive, and our confidence interval is negative instead of positive because the mean difference is negative. So what it does when it runs the t-test is it takes the first score that you put in minus the second score. Well, when you're looking for an improvement, I would always run this as what I'm measuring second I would run it this way. I think positive numbers are just easier to interpret. However, let's say we were doing something, maybe a weight loss program, and we have a before and after weight. Well, if the weight loss program is working, you would expect the measurements that are taken from pre-status to be more than post-status. So in that situation, I think it would be better to put pre first and post second. I try to keep my measurements positive because I think they're easier to interpret that way. All right. Well, guys, at the end of the day, I guess that's all I got for you. My battery's about dead on my iPad, so I'm going to call it a day. All right. Take care.